In this video, we're going to talk about squeeze theorem. The squeeze theorem is something you would apply to limits. It's another way we could calculate a limit. I must say it's used in much more niche situations. It's not something you use on many problems. It is a tool you want in your pocket, though. For example, if you're taking the AP test for calculus, they can give you a squeeze theorem problem. And the harder part is they won't even tell you it's a squeeze theorem problem. They'll just say calculate this limit. And the only way you can do it is by using squeeze theorem. So really quick, let me define squeeze theorem, then I'll motivate why it's useful. So it goes like this. It says if you have this function here, f of x, and it's less than or equal to g of x, which is then less than or equal to, let's say, h of x, when x is near a, you'll see where a comes in a second, and the limit of these outside ones, so f of x and h of x, sorry, this is x goes to a, is equal to L. So what I'm saying is if this function g of x, and I'll point it out specifically that we're really involved with this guy here, if this function is between these two values for their y value, and we know the limit of this guy and this guy are the same, then it has to be the case, so I'll put then, it has to be the case that the limit of that middle function is the same as the outside ones. It's going to be equal to L. Okay. So here's the theorem. We're going to go through an example just so you can see how it's used. Like I said, it's not used in a lot of problems. The general rule of thumb is you will use this when you have weird limits with trig functions, okay? Reason being is we know direct substitution from the last video, you can just plug in values. The issue with trig ones is if you plug in the value and you get it divided by 0, there's not a good way to clear that out. So let's go into an example here. We're gonna go with, okay, let's find the limit as x goes to 0 of this guy here. Sorry, x squared sine of 1 over x. Okay. So in our last video, we talked about direct substitution. Let's go ahead and try it here, right? So let's plug in 0. We would get 0 times sine of 1 over 0. And that's an issue. Okay. Sine of 1 over 0, I can't even do 1 over 0. If you put that in a calculator, you're going to get nothing, right? And so at that point, we're stuck. Okay, so we know direct substitution is not going to work. And the even harder part is how do we even simplify this so that we could do direct substitution? We really can't. So that's when we're going to turn to squeeze theorem here. Okay. And so just to phrase it right, if we look at squeeze theorem, the idea is we need to find these functions that bound what we have here. Okay. And you'll get used to it. So let me start writing it out and you'll see how it works. So really quick, let's just talk about sine of x, okay? If you look at a graph of sine of x, you'll see that its output is between 1 and -1. So if I draw a little graph of it, this isn't going to be a perfect graph, but here's 1, here's -1. Sine graph looks something like this, right? Repeats. Okay. Oops, I don't know why it erased it there. Let me draw that again. It looks like this, right? And so we know it's always between 1 and -1, like this. The same is also true for sine of 1 over x. Okay, so if you put that in Desmos, you'll see this is also the case, that it's between these two values here. Okay. Why is this useful? Well, let's talk about these boundaries here, because I've got an idea. Let me erase this graph so we have a little more room. The idea is we want this middle function here to look like what we have here, because if we can get it bound on two sides, then we're good to go. So what we need to do in this case, right, if you look at the difference, is let's multiply everything by x squared, okay? Gonna give us this here. And yes, that does work for this inequality in this case. So then we have this here, okay? So we're saying this function that we had here, this one here, is bounded by x squared and negative x squared, okay? Now let's talk about why this is useful. Well, let's take a look at this guy here. Let's get its limit. If I do the limit of negative x squared as x goes to 0. I can do direct substitution. That's just going to be 0, right? Let's do this one as well. The limit as x goes to 0 of x squared. That one's also just 0. Just plug it in, right? So what we're seeing is our function that's right here is bounded, so it's squeezed between these other two. And these other two, their limit is 0. And so if this is squeezed between it, this also has to have that same limit. It must be the case that the limit of this guy, this middle function, is x squared sine of 1 over x. It has to be 0. And that would be our answer in this case. It's going to be equal to 0. To motivate it even more, if I draw a graph, is it'll look something like this. I know my functions between x squared and negative x squared. So here's x squared. Here's negative x squared. Our sine graph will look something like this. You can put it in Desmos if you want to see it, but it goes like this, goes up and down like that. Oh, and erased again. There we go. And so you'll see this is how the squeeze theorem works, is I know the limit of this top u, I know the limit of this bottom u at 0, and our sine function squeezed between it, so it has to have that same limit of 0, right? So it's tricky. It's not, like I said, it's not used very often, this squeeze theorem, but it is a good one to know. Your giveaways, you're typically working with sine or cosine. Let's just do one more example really quick so you can see it. You'll get the hang of it. So this could be on like the AP test, for example. It'll say find the limit, x goes to 0, and you'll see it's very similar to what we just did. Let's do x cosine of 1 over x. Okay. Same idea. If I plug in 0, I'm going to be dividing by 0, so I know direct substitution is not going to work. Got to do something differently, right? It's going to be squeeze theorem because you're dealing with trig. And so it almost always starts like this, that our trig function is between these two values here, 1 and negative 1. Okay. This also applies to cosine of 1 over x, which you can always verify in Desmos if you want to see that. Okay, then I multiply both sides by x so that we get something like this. That looks just like our limit now. And now I take the limits of these sides here. So the limit, oops, sorry, this should be an x, not a 1. Let me fix that. Because we multiplied by x. Now if we do the limit of those n pieces, really easy. This one will be 0. Limit of this one here is also 0. And so it has to be the case that the limit of this guy here in the middle is 0. So once again, this is squeeze theorem, right? It's just a tool you can use on certain problems that can't be solved any other way.